Alright, let's continue our discussion of how we work with things in binary. And we're going to continue to see that this parallels what we do with, sort of plain old decimal numbers, starting with addition. So suppose I want to take the number 25 and I want to add the number 13, where these are decimal numbers. So we can do our conversion by dividing by 2 and so on. And what we'll find out is that 25 looks like 25 decimal is 16 plus another 8, no 4s, no 2s, and a 1. And 13 looks like an 8 and a 4 is 12 and a 1 is 13. And let me just put some zeros in the front here. So I have two 6-bit numbers. This is the number 25, this is the number 13. Now if I want to add these in binary, I can do exactly the same thing I do when I add plain old numbers in decimal, which is to say add each pair of digits. 1 plus 1 is 2. Well, remember 2 in binary looks like 1, 0, so this is like adding 5 and 5 and getting 10. We take the 0, we put it here, and then we take that extra 1 and we put it up here as a carry, right, into the next column. 1 plus 0 is 1. And this time there's no carry, so we just do 0 plus 1 is 1. 1 plus 1 again is 2, so it's like 10. We put the 0 here and we put a carry up top. And now 1 plus 0, well, that's again 2. So we put a 0 here with an extra carry into the next column. 1 plus 0 is 1. So by adding these two numbers in binary, we get this number. And what is this number? This is 32 plus 4 plus 2, which is 38. Well, that's what we would get if we added these two numbers in decimal. 5 and 3 is 8, 2 and 1 is 3. So addition of numbers works exactly the same way in binary as it does in decimal. So that's helpful, and this is actually one way we can design a circuit for adding numbers, which we'll do a bunch of in this course. So addition works the same. Multiplication also works the same, except it's in some ways easier, in some ways more difficult. So suppose I want to do 5 times 4. So here's what the number 5 looks like, here's what the number 4 looks like. Well, 0 times 101, that's just going to give me 0. 0 times 101, that's going to give me 0, and I shifted over 1. 1 times 101 is going to give me 101, and I shift it over. And then when I add this up, I get 0, 0, 1, 0, 1. And sure enough, this is equal to 16 plus 4, which is 20. That's 5 times 4. So it's easier because, if we have a 0 here, multiplying our number by 0 leaves us with 0. If we have a 1, multiplying this number by 1 just takes this number and puts it down there. So it's an add and shift, but the add part's not really very significant. It's really just, write this number down in different positions, and then at the end go through and add all of these. And so multiplication works the same. We can also do division, we can also do subtraction. However, it turns out there's an easier way to do subtraction. And remember, if we want to do something like 5 minus 2, we can think of this as an addition problem where we take 5 and we add negative 2 to it. Now so far we don't have a notion of negative numbers in binary because we're adding powers of 2, 1, 2, 4, 8, 16. We always get a number that's bigger than or equal to 0. So let's ask this question, what is negative 1 in binary? Alright, so very important point. Anytime that we're working with negative numbers, it's going to be really important that we decide how many bits we're using. Now, when we're writing positive numbers, if I want to write the number 5, I can write this. I could also write this. I could also write this. And all of those mean 5. And there's no question about that because the leading zeros don't make any difference. Just like in decimal, I could write 5 or, 005. And it would look weird, but all of us would agree these are the number 5. But when we have negative numbers, we've got to fix how many bits we're going to use. So let's fix a 4-bit notation. So every number we write is going to be 4 bits. Alright, so what does the number positive 1 look like? It looks like this. So how do we define negative 1? Negative 1 is the thing that, when added to positive 1, results in 0. So we're going to find a way to write negative 1 by asking the following question. If I start off with positive 1 and I add something to it, what should I add to end up with 4 zeros? Well, you know, I've got a 1 here. What should I add to get a 0? If I add a 0, I'm going to end up with a 1. So I have to put a 1 here. And 1 plus 1 will give me a 0 with an extra carry. And now I've got a 1 plus a 0 plus something. Well, this is going to have to be a 1. This will give me a 0 with an extra carry. Same thing here, 1 plus 0. This is going to have to be a 1. That'll give me a 0 with an extra carry. And a 1 plus a 0, I'll need an extra 1 here. That'll give me a 0. There'll be an extra carry coming out on the end. We're just going to ignore that. Why? Because we're doing 4 bits. So even though our answer overflowed, we're going to say that 1 plus this number is equal to 0. And therefore, this number means negative 1. So that's the convention we're going to use. So when we want to write a negative number, we're going to figure out what number you add to it to get you to negative 1. So let's try that again. Let's say, what is negative 2 in binary? Well, let's write the number 2, and then we want to add something and end up with all zeros. Well, 0 plus 0 will get us 0. 1 plus 1 will get us 0 with a carry of 1. 1 0 plus 1 will get us 0 with a carry of 1. And 1 plus 0 plus 1 will get us a 0 with that final carry. So therefore, 1110 means negative 2. So we've got 1111 to mean the number 1, and we've got 1110 to mean the number minus 2. Alright, well, we can generalize this. Instead of actually writing these numbers down and trying to add, we can generalize. So given a positive number, let's call it n, negative n is found by, first, complement each bit of n and then add 1. I'll leave it to you to think about this analysis of what do we add to this to get a 0 out on the end, and why complementing each bit and adding 1 at the end will achieve that goal. But let's see what this does. So positive 1 looks like 0, 0, 0, 1. Negative 1, toggle each bit, add 1. That's what negative 1 is. Positive 2 looks like this. Negative 2, we would toggle each bit, 1, 1, 0, 1, and then add 1, and it gets us 1, 1, 1, 0. Positive 7 looks like this. To get negative 7, we would complement each bit, and then we would add 1, and we would get this, and this is what negative 7 looks like. So this is called 2's complement notation. And 2's complement notation does not mean that we're looking at a number that's negative. It means that when we look at a number, it could represent a positive or a negative number. And it turns out the way that we can tell is by looking at this most significant bit. This bit right here, if it's a 1, then we have a negative number. If it's a 0, we have a number that's not negative, bigger than or equal to 0. And just as kind of a sanity check, if I write the number 0, I get 4 zeros. If I try to express negative 0, what would I do? I would complement each of the bits. I would add 1. It's going to come back to 0. So negative 0 and positive 0 look exactly the same, which is good. That's what we would hope would happen. All right, so what does this look like if we write out all of our numbers? So 7 looks like this. The positive numbers look the same as always. The negative numbers come out like this. So there's the 2's complement representation of all our numbers from -8 to +7. You'll also note that if I take this as just a plain old unsigned number, 12, and I add this number 4, I get 16. If I take this number 9 and I add this number 7, I get 16. So we're seeing another way to interpret why this pattern of bits corresponds to this negative number. Because if I add this thing to it, I get to 16, and in 4 bits, 16 looks like 4 zeros. That extra 1 falls off the end. So, so this is for 4-bit 2's complement. And you notice we can represent numbers from -8 to +7. It's not symmetric. We cannot do +8. Why? Because if I tried to write +8, first of all, that 1 there would say, hey, this number should be negative. But if I tried to complement it, I would take all of these bits, I would invert them, I'd add 1, I'd end up with the same bit pattern. So we cannot validly represent the number +8 in 4-bit 2's complement. We can only go up to +7, but we can do -8. All right, so why is this useful? Because with this approach to negatives, subtraction works by addition. So for example, if I want to do 5 minus 3, that's just 5 plus -3. So what's the number 5? 0, 1, 0, 1. What's the number -3? 1, 1, 0, 1. I'm going to do plain old addition. 1 plus 1 is 0 with a carry. 1, 0, 0 is 1. 1 plus 1 is 0 with a carry. 1, 0, 1 is 0. We have an extra carry coming out of the end. But here's our answer, 0, 0, 1, 0. And that's the number 2. Well, that's what 5 minus 3 is. If I do 3 minus 5, that's 3 plus -5. Well, our number 3 is 0, 0, 1, 1. Our number -5 is 1, 0, 1, 1. And when I add those, 1 and 1 is 0 with a carry. 1 and 1 and 1, that's the number 3, which is 1, 1. So I write down that 1, and this becomes a carry. 1, 0, 0 is 1. No carry in here. This gives us a 1. Our answer is 1, 1, 1, 0. And 1, 1, 1, 0. That's -2. So 3 minus 5 is -2. So by using this notation, taking subtraction is simply the addition of negative numbers, works perfectly fine. And it works with negatives as well as positives. If I wanted to do -1 minus 1, that's -1 plus -1. Well, here's -1. Here's another -1. If we add those together, 1 and 1 is 0 with a carry. 1, 1, 1 is 1 with a carry. 1, 1, 1 is 1 with a carry. 1, 1, 1 is 1, and we have an extra carry. We get this answer, which again is -2. Well, -1 minus 1 is -2. So if we choose to represent negative numbers in 2's complement, we don't have to treat negative numbers differently from positive numbers. Addition still works the way that we would expect. And so that's helpful. And so this is the most common notation that we'll use for storing negative numbers in binary. But it's not the only one. There are other ways that we could represent negatives. One method we'll see sometimes is what's called signed magnitude. And in signed magnitude, if this is what positive 5 looks like, negative 5 is the same thing, but we just make that first digit a 1 instead of a 0. And so we again use this idea that 1 means the number is negative, a 0 means it's positive, but the remainder in this case we just treat as a plain old unsigned number, and we say 1 plus 4 is 5. So 2's complement, negative 5, is 1, 0, 1, 1. Signed magnitude, it's 1, 1, 0, 1. And this is what we do in decimal numbers, right? How do we write negative 137? Well, we write positive 137, and we put a special symbol in front. Instead of a space, we put this dash that makes it negative. So this is what we do as humans with decimal numbers, but mostly what we do in a computer is 2's complement notation. All right, so the other thing we can do, now that we know 2's complement, is we can talk about overflow. And you know, sometimes when we add numbers in a computer, the answer is too big to fit. We don't have this problem on paper unless we run out of, space on the side of the page. And that's kind of what happens in a computer when we add binary numbers, because the memory in which we store the bits of a number has a fixed amount of space. So again, if we're thinking about 4 bits and we want to calculate something like 9 plus 10, and this is just plain unsigned numbers, so let's do unsigned as opposed to 2's complement. Well, 9 looks like this and 10 looks like this, and when we add those, 1 and 0 is 1, 0 and 1 is 1, 0, 0, 1, 1 is a 0. We get that carry out at the end. For unsigned numbers, that tells us our answer is too big. Our answer really should have been 10011, which is 19, but the biggest number we can represent with 4 bits is 15. But for 2's complement, we do something slightly different. Suppose I want to take the number 5 and I want to add the number 4. So here's the number 5 and here's the number 4. And when I add those together, 1 and 0 is 1, 0, 1 and 1 is 0 with a carry. There's a 1. We look at the answer, and here's how we know that we have an overflow, because we added 2 positive numbers, positive 5 and positive 4, and our answer, this bit here, tells us that our sum is negative. Well, if you add 2 positive numbers, you should get a positive number. If you get a negative number, you've got overflow. And similarly, if I were to take 2 negative numbers and add them together, so for example, let's take the number negative 1, which is 1111, and negative 8, which is 1000, and add those together. And what do I get? I get a 1, 1, 1, 1, and 1 is a 0. And my sign bit, this tells me that my sum is not negative. But I added 2 negative numbers, I should get a negative. So since my sum is not negative, I have an overflow. So when we're doing 2-bit signed representation and we add 2 numbers, if we add 2 positives and our sum is negative, it's an overflow. If we add 2 negatives and our sum is not negative, it's an overflow. If we add a positive and a negative, we cannot get an overflow. The way the numbers work out, our number will always fit within the range. but two positives, two negatives, your sum has to have the same sign as the things you were adding. If it doesn't, it's an overflow. And it's not this fifth bit that tells us, right? It's the sign bit of our, in this case, 4-bit representation. So that's something to keep in mind with addition circuitry. All right, so let's go back and look at truth tables. And let's start connecting truth tables, which are kind of this theoretical way of, describing behavior of a circuit. Let's start connecting this with something real world. So an example I want to use is a combination lock. And let's say that we want to build a circuit that has 3 buttons on it. I'll call them A, B, C. And if you press the right set of these buttons, I want to unlock a door. So I can draw something like a system diagram. I'm going to have 3 buttons coming in. I'm going to label them A, B, C. I'm going to say A, B, and C input buttons. 1 means that the button is pressed. 0 means it's not pressed. And I'm going to have a single output X is an output. And 1 means unlock. 0 means lock. So, maybe this is how we get into our Tesla or something. We have 3 buttons on the side, and if you press the right set of buttons, this circuit will generate a 1, unlocks the door, and you can climb inside. All right, so how would we design a circuit to do this? It depends on what we want our unlock combination to be. So let's look at all the possibilities. And this is a super secure system because there's effectively 8 passwords and nobody will ever be able to guess what our password is. So suppose that, you don't want to try to remember anything too complex, and so we're going to say, okay, my secret password is press all 3 buttons at once. So in this case, I want my output of my circuit to be a 1, and in all the other cases, I want my door to remain locked. All right, so inside this box, the system diagram, I want to build a circuit. It takes in these 3 inputs and generates this output, and I want this truth table to be a description of how the circuit behaves. Well, what could I possibly do to create a circuit that outputs a 1 when A, B, and C are 1, and a 0 in all other cases? And if you think about it and you go back to truth tables you've drawn, you realize this is nothing more than an AND function. If we write something like x equals A, B, C, we can literally translate that as x is A and B and C. And when we say A, what we really mean is A is equal to 1, and B is equal to 1, and C is equal to 1. And that's exactly this case right here. And that's the only case where x is going to be a 1. In any other case, x will be a 0, the door is locked. So there's a logic equation, and we could turn that into a circuit, which we're going to do next. We can turn that into a circuit and put that inside our box, put in A, B, and C, take out the output X, and we've got our door control system. All right, now suppose that you also want to have a friend have access to your car, but you don't want to give them your password 111 that you use for everything else in your life. So you want to give them a different password. So maybe we're going to give them the password 111. So we also want our circuit to output a 1 if the input is 101. Well, we lucked out in this case because we have a gate which outputs 1 when exactly all 3 inputs are 1. We don't have a gate that we've encountered so far that outputs a 1 when these 2 inputs are 1 and this input is a 0. But we can use a gate that we already know about, an AND gate, and achieve this behavior with just one simple change. We want our output to be 1 when A is 1 and B is 0 and C is 1. So we want, let's look at this up here, we want x equal 1 when A equals 1 and B equals 0 and C equals 1. Well, we don't have a gate that checks these three conditions to see if they're all true, but I can rewrite this condition as saying the complement of B is equal to 1. And I can say, hey, I want x to be 1 when A is 1 and the complement of B is 1 and C is 1. And I do have a gate that will tell me when this situation is true. It's just this. It's an AND gate with this middle input inverted. And sure enough, if I look at all 8 rows, there's only one row where this expression A, B bar, C turns out to be true. And that's when A is 1 and B is 0 and C is 1. That's this row right here. Alright, so here's the kicker. If I want my output x to be true in either of these cases, I want x to be 1 when A and B and C are 1, or when A and C are 1 and B is a 0. And this equation generates this truth table perfectly. And if we wanted to add a third expression, we could figure out some AND expression that was true for that particular set of inputs, and we could OR that along with these two expressions, and we'd have a new equation that would generate that truth table. All right, so that's the motivation for what we're doing here. Let's look at the mechanics of it, so that we can do this more quickly in the future. So there's our 8 possible sets of inputs, and suppose we want a 1 here, here, and here. And we want to write an equation for x. So here's how we do this. First of all, find each row where x should be a 1. And we're going to write down some kind of product involving A, B, and C. But if we want the value of A to be a 0, put a bar on top. Want it to be a 0, put a bar on top. Want it to be a 0, put a bar on top. And by the way, this is not the same as this. So if you're doing this, make sure there's a space in between those bars, otherwise it looks like this, and you've got a different equation. Alright, here's another row where we want a 1, so I'm going to do A, B, C. I want A to be a 0, I want C to be a 0. Here's another case where we want our output to be a 1, so I'm going to write A, B, C, and we want A to be a 0, I'll put a bar up there. Here's a fourth case where we want our output to be a 1, so I'll write A, B, C, and we want C to be a 0, I'll put a bar on top. And here's a fifth case, I'll write A, B, C. All of these are 1, I don't put a bar anywhere. And so if you were to generate a truth table for this equation, you would get exactly this truth table. And this is called a sum of products. Sometimes called an SOP. Why? Each of these 5 expressions we can think of as a product, a set of multiplications. It's really a logical AND, but ANDing kind of looks like multiplication. And then those 5 products, we sum them. We put a plus sign in between. It's an OR, but it kind of looks like addition. So it's a sum of these 5 product terms. And this is the most common way to write an equation from a truth table. Alright, so we can do this for any truth table. If we had 4 input variables, we would write A, B, C, D, and anywhere that our variable was supposed to be a 0, we'd put a bar on top. Well, this is great, and this is, easy to understand. If we've done 120 and we remember what these symbols mean, we can go from this to a truth table. But this starts to be inconvenient when you do this a lot. And every time that we have a truth table and we try to write an equation, it's the same thing. If there's a 1 here, it's going to be A bar, B bar, C bar. and so on and so forth. So there's a shorthand that we develop, and the shorthand is to use what are called minterms. And instead of writing A bar, B bar, C bar, we write the symbol lowercase m with a subscript of 0. And we call that minterm 0. Here's minterm 1, minterm 2, and so on. And now we could say x equals minterm 1 plus, minterm 0 plus minterm 2 plus minterm 3 plus 6 plus 7. Alright, there's one thing missing from this, which is when I see minterm 3, how do I know that that's A bar BC as opposed to C bar BA? In other words, the order of this ABC makes a difference as to what minterm 3 looks like. It's a minterm 3 because this is a 0, this is a 1, this is a 1. But if I wrote my columns with a C and a B and an A, well, this would be the case where C was 0, A and B were 1. And from what I've written here, there's no way to tell that. So we usually write X parentheses and we list the inputs in the order that they are in the truth table. So now when I see minterm 3, I know that corresponds to input values of 0, 1, 1. It's the A that's a 0, and the B and the C are 1s. And that lets us go from this expression back to this expression. Alright, well, we write this often enough that we can use an abbreviation to make this simpler. Sometimes we just write a summation sign for sum, and we say 0, 2, 3, 6, 7. And this is about the most succinct way of writing an equation for this truth table. And it captures all the information that's in here, it captures all the information that's in here. Because when I see something like this, and I know it's a sum of products, right? The sigma tells me it's a sum, and I'm just going to write the minterm corresponding to each of these subscripts. Minterm 0, it's going to be A bar, B bar, C bar. Minterm 2 is going to be A bar, B, C. Minterm 3 is going to be A bar, B, C, and so on and so forth. So lots of practice questions to give us some practice going between truth tables, Boolean equations, sums of minterms, and this compact form. And let me give you some terminology here. You'll see this in assignments and stuff. This is called standard or canonical form, or sometimes full form. And these are called compact forms. This is implicit, this is explicit, but they're both compact forms. And sometimes, you know, we'll ask you to write an equation in compact form. That means you can use this abbreviation. Sometimes we'll ask for the standard or canonical form, and that will be this equation where you actually write each of these product terms with an A and a B and a C and so on. All right, so this is the shorthand, that's the compact form. Alright, and this works for any number of variables. If we had 4 input variables, our minterms would go from 0 to 15. If we had 6 input variables, our minterms would go from 0 to 63. So if I wanted to go back to our combination lock circuit, I could write an equation for x in compact minterm form and just say x equals sum 5, 7. And that but let me do what I said you had to do. Let me list the order of the input variables. So x parentheses ABC equals sum 5, 7. That captures all of this information, captures all of this information. All right, So that's a sum of products. In terms of min terms and in terms of, you know, actually writing out the product terms. All right, so what have we been doing in this video? We've been developing a process. We are developing a chain starting with some sort of design goal that we're after. Hey, I want a combination lock that unlocks my door with this input or that input. From there, we write a system diagram. And the system diagram is where we kind of pin down, you know, what are the inputs and the outputs? What do the ones and zeros mean for those? And then from there, we can capture the behavior by writing a truth table. Once we have a truth table, we can write a Boolean equation. Or equations if there's more than one output. And from the Boolean equations, we can now make a circuit diagram. And so this is the last step of our process. And from the circuit diagram, we could either, you know, go into Tinkercad and build that circuit, or you could hand a diagram to an engineer who could assemble the circuit for us, or we could put it into a piece of software that would talk to a machine that gets components and builds them onto a circuit board and so on. This is usually the step that we end with, unless we're doing a lab and then we're actually, you know, implementing the circuit. So the last thing we want to talk about today is this circuit diagram. And let me start with a simpler example than the last one. Let's go back to our original combination lock. And so we want a circuit that implements the following equation: x equals a, b, c, or a, b bar, c. All right, there's two steps to building a circuit diagram. Right? The first is to figure out what the logical elements are that you're going to use, and then the second is actually coming up with a wiring diagram. And I'm going to kind of do these two things together, but it's a developmental process. This is something you normally want to do with, you know, a nice clean sheet of paper, a good sharp pencil, a good eraser, and you can plan on probably doing this twice for most circuits. The first time to figure out what your circuit should look like, but that's going to include, you know, corrections and extra lines and scribbles and things like that. And then once you've got it laid out, you'll probably want to make a nice clean version of your circuit. And yeah, there's software that will do a lot of the heavy lifting for you, but you really want to develop the skill of doing this by hand. It's a good way to you know, help get clarity over what it is that you're trying to do, and help sort of solidify those concepts. So let's start with ABC or A, B bar, C. And we could just start, you know, putting some AND gates down on paper and just sort of, you know, connecting the lines. But let me show you a methodical way of doing this. So we know the inputs are A, B, C. We know that because we also drew a system diagram. So I'm going to put my inputs over here like this. I'm going to run a wire down underneath each input. And then near the top, I'm going to take each of these inputs and put it through an inverter and run a wire down from there. So now I have 6 lines running vertically on my page. This is A bar, B bar, C bar. And I'm going to label these at the bottom just to remind me. And now I'm going to start writing my product terms. Well, I need a product term for A, B, C. So I'm going to draw a 3-input AND gate. And I want the inputs to be A, B, and C. Well, I've got A right here, B right here, C right here. So I'm just going to draw a line over to A going to put a dot there showing there's a connection, because there's no connection between this line and B, right? It's just kind of crossing over that. But the dot says, yeah, there's a connection right there. I want a second input to be B. I want a third input to be C. And so this output right here, this is ABC. Now I also want to generate A, B bar C, so I'm going to draw another AND gate. And I'm going to connect the inputs from my vertical input set. So one input's going to come from A. The second input's going to come from B bar. Well, that's this line right here. So I'll make a connection to that. And the third input comes from C. That's right here. So this is A, B bar, C. So this line is the first term. This line is the second term. What do I want to do? I want to OR them. So I need to put them into an OR gate. So I'll draw an OR gate. And there's my output X. All right, so this is a good logic diagram. But to actually make a wiring diagram that somebody could use to turn this into a working circuit, we need to do a few other things. So, you know, this is supposed to be an AND gate, but we don't find these little, you know, semicircular things with dots in the middle in our parts box. What we find is chips, integrated circuits. So we're going to go back to engrcs.com, and we're going to go over to component specifications, and we're going to look for something like a 3-input AND gate. Well, there's a 2-input AND gate, there's a 4-input AND gate, there's a 3-input NAND gate. We have a choice. We can either build this 3-input gate out of a couple of 2-input gates, and that's not a hard thing to do. If I want to do ABC, I can do that by doing A, B, ANDing that, and then ANDing that with C. Alright, this is because the AND operation is associative, so we can AND A and B together first and then AND that with C. That's just ABC. Or if we had a 4-input AND gate, I could take C, for example, and feed that into both inputs. And now my output will be A ANDed with B, ANDed with C, ANDed with C. Well, we know that this is the same as this, and we know that C ANDed with itself is just C. So this is another way to get a 3-input AND operation out of, in this case, a device with 4 inputs. Well, since I already started drawing this picture before I looked up my parts, bad mistake, I'm just going to go ahead and think of this as a 4-input AND gate. Think of this as a 4-input AND gate, and I'll just take one of the inputs and feed it into 2 of the inputs of the AND gate. So that's going to let me work with my 4-input AND gate, which is a 74LS21. Alright, so here's what the chip looks like. So the next thing we need to put on our schematic is something called a component ID block. And the idea is each of these chips, each of these gates is going to come from some sort of physical chip. So I have a 74LS21, that's a dual 4-input AND gate. So I'm going to take both of these from a single 74LS21. Now I don't want to write 74LS21 here and everywhere else. So I use a symbol, and the symbols we use are the letter U followed by a number, starting with 1 usually. So these gates will come from a component which we're going to call U1. And so up here in my component ID block, I'm going to list the ID of a component, the type of device it is. I'm also going to list where power gets connected, where ground gets connected, and which pins have no connection anywhere. So my first component is going to be U1, and that's a 74LS21. And I'm going to look at my picture of this device, and I'm going to say, okay, ground is on pin 7, VCC is on pin 14. So VCC is 14, ground is 7. I'm going to use all 4 inputs into this gate and the output. Pin 3 has no connection to anything, so I'm going to list that as no connection, and pin 11 has no connection. So no connection will be pins 3 and 11. And now I'm going to label the pins on this first 4 input AND gate. And so I can use these 4 inputs in any order that I want, but they come from pins 1, 2, 4, and 5. So next to each of these, I'm just going to write a small number, 1, 2, 4, and 5. To say, hey, those are the pins I go into on chip U1, which is what? A 74LS21. And the output comes from pin 6, so I'll put a pin 6 right here. Alright, my second 4 input AND gate, that's going to use this other gate inside, and the inputs there are pins 13, 12, 10, and 9. So I'll label these 13, 12, 10, and 9. And it doesn't matter what order I did those in. And then the output from this is on pin 8, so I'll put an 8 over here. Here's my output pin. So now if somebody sees this diagram, they know, okay, U1, I have to go and I have to get one of these chips, put it into my board, hook up power and ground. All right, pin 1 is going to go over here, pin 2 over here, pin 4 and 5 are going to go over here, and so on. All right, I have a second gate. I have this OR gate, so I'm going to label this U2. I'm going to add that to my component ID block. And let's find a 2 input OR gate. So it looks like right here, that's a 74LS32. So that's my next component. And again, most of these are the same, not all of them. Ground is on pin 7, VCC on 14. And this one has 4 OR gates inside. Well, I only need 1 OR gate right here. So I can pick whichever one I want. Let's just pick this lower left one. So my inputs are pins 1 and 2. My output is pin 3. So I'll label this 1 and 2 and 3. And now I have a lot of unused pins. 4, 5, and 6 are unused. So I'll list 4 through 6 as no connection. 7 is our ground. 8 through 13 are also unused. So I'll list 8 through 13. So now at this part of the circuit, the engineer says, oh, U2 7432 grabs that chip, puts it in the board, connects power and ground. Oh, pin 1 of this chip goes to pin 6 of that. Pin 2 of this chip goes to pin 8 of that, right? And they don't need to be thinking about, truth tables or sums of products or anything like that. Now it's just a recipe. It's just a mechanical process of following what this diagram is telling you to do. All right, we have one more set of gates to deal with. We have these inverters over here. So let's find an inverter, and that's a 7404. And they look like this. Oh, okay, so it's a different kind of picture that they're showing us here. We have to look at the function table and see A is the input and Y is the output. And there's 6 inverters. One of them goes from pin 1 to 2, another from 3 to 4, another from 5 to 6. Another goes from 9 to 8, 11 to 10, and 13 to 12. So this is going to be our last component, and these are all going to be labeled U3. And U3 is going to be a 74LS04, VCC on 14, ground on 7. And let's pick some pins. Well, our first one, let's just go in on pin 1, out on pin 2. So this is a 1 and a 2. Our second one, we can go in on 3, out on 4. And our third one, in 5, out 6. And then all of the other pins over here from 8 through 13 are unused. So we'll list those as no connection. And now we've got all of our gates specified. And again, U3, okay, get a 7404, put it into the board, connect power and ground. And then pin 4 of U3 goes to pin 10 of U1. So you take a wire and you plug it into those corresponding holes, and so on. This is how you build your circuit. All right, the last thing, if we're actually designing a circuit that we're going to be able to test using buttons and an LED, is to add those components. So for our output, we're typically going to go through an LED and then a resistor 1 kilo ohm and go to ground. And that's all we need. We don't need to list a component ID for this. This is the universal symbol for an LED. This is a symbol for a resistor, but we have to say what the resistance is. And you want to use this squiggly line for a resistor. If you go online and you use a website to build a circuit, a lot of times they'll do something like this for a resistor, and they'll label it, right? Don't do that. Use the symbol that we use for schematics. Use this symbol for an LED. All right, what about the input switches? So remember, there's a standard way we talked about wiring a switch, which is to take an input, pull it through a 1 kilo ohm resistor to 5 volts, and then use a switch. So we have the option of pulling this input down to ground. So I didn't leave myself a lot of space up here, but let's do the best we can. Let's take input A, and let's connect that to 5 volts through a 1 kilo ohm resistor. Let's do the same thing for input B. And so you can see where I'd like to have used a pencil for this. And let's take C, connect that through a 1 kilo ohm to 5 volts. And then each of these inputs we're going to control with a switch. So we're going to take a switch here, connect this to ground. That's our input A. We're going to take this point, have a switch we can use to connect that to ground, and then point C, we'll have a switch to connect that to ground. So this is horribly sloppy at this point, right? But like I say, you do this part of it on scratch paper first, and then you draw it more neatly. But this has the required ideas, right? So C is controlled by a switch. If I close this switch, I'll get a 0 right at this point. If I open the switch, I'll get a logic 1 at this point. And then, you know, this is C bar, and so on. So a lot of steps in the process, right? Designing a good circuit takes a lot of time. Slapping down a few gates on paper does not take as much time, right? If someone says, hey, can you make me a circuit to do this equation, I could do something like this, right? X equals ABC or AB bar C. Yeah. Alright, there we go, we're done. That took about 20 seconds instead of the 15 or 20 minutes we've been spending. This is technically a good logic diagram for that circuit, but it's not a lot of use when you're actually trying to build this circuit in Tinkercad or on a physical protoboard. This is extremely useful. And the other advantage of this is extremely useful for debugging your circuit. Because when you're finished, you've got your circuit and you set up a certain combination of switches and you expect your LED to come on, and let's say your LED is off instead of on. Well, you can get a multimeter and you can take a voltage reading right here and say, what's the voltage here? If this is 5 volts, something's wrong with your LED. All of this circuitry is correct because this is generating the correct 5 volts, but your LED is not lighting. Maybe it's backwards, maybe it's a bad LED, maybe it's not connected to ground through a resistor. Maybe this is a 1 mega ohm resistor instead of 1 kilo ohm. But you've isolated your problem to somewhere right here. But if you take your multimeter and you measure this and you see a 0 coming out and you expected a 1, there's a problem somewhere in here. Well, so you go to pin 3 of chip U2 and you measure the voltage. If that's a 3, there's just a problem with this wire. If that's 5 volts and if this is 0, then there's a problem with this connection. But if pin 3 is actually reading 0, well, that's a problem, right? We expected this to be generating a 1. Well, if we go back to our equation, maybe that's because one of these inputs should be a 1. So now we take our multimeter and we measure the inputs. If one of these is a 1 and the output is a 0, there's a problem with that gate. Maybe it's not powered correctly, maybe it's not plugged into the board correctly, maybe it's a bad chip, maybe it's not really a 74LS32. But if both of these inputs are low and we expected, say, this one to be high, then there's a problem somewhere in this part of our circuit. So we're narrowing down where the problem is. Okay, suppose we expected the output of this AND gate to be a 1. That means we expected all 4 inputs to be a 1. So take a voltage reading at pin 8. If that's a 0, this is not connected to here. Right? Or if that's a 1, then this is not connected to here. If we're getting a 0 volts at pin 2 and we're getting a 1 here, it's a bad wire. Or maybe the wire's in the wrong place. But if we're getting a 0 out on pin 8, then there must be at least one of these inputs which is also 0. So now we take voltage readings on pins 9, 10, 12, and 13. And let's say pin 10 is low instead of high. Well, where does pin 10 come from? It comes from pin 4 on U3. So take a voltage reading there. If we expect this to be 1 and it is 1, and it's a 0 down here, there's a problem with that connection. If this is a 0, then there's a problem somewhere here. And we can keep tracing our circuit back. And eventually we're going to find some point where we say, hey, this should be 0, but it's a 1. Or it should be a 1, but it's a 0. And there's some undeniable reason for it. For example, the output here should be 1, but it's a 0. But the input is a 0. So this is an inverter that's got a 0 going in and a 0 going out. That's where your problem is. So what's the problem? Is it that this is not actually an inverter? Is the inverter bad? Did I put in the wrong type of chip? Did I forget to connect power and ground on pins 7 and 14? And we can spot check our circuit, right? When we're studying U3 and trying to figure out what's wrong, we can eyeball it and say, make sure there's no wires between 8 and 13. Well, if we see a wire going into pin 10, we know something's wrong. And we go and we check our wiring and it's like, oh, this was supposed to go in pin 3. It actually got put in pin 10. Well, you just found your problem. So this is really, really important. And anytime that you are building a circuit and it's not doing what it's supposed to do, and you ask someone for help, the first thing they're going to say is, let me see your wiring diagram. If you don't have a wiring diagram, there's no help, right? You got to have this written out before you can debug your circuit. And you have the option of pulling all the wires out and throwing the board on the floor and getting a new board and starting over. That's not effective, right? It might feel good in the moment, but it's not an efficient way to find the problem. If you've built your circuit from a wiring diagram, you can debug it. If you're computer science, this is very much how we debug programs. You write a 1,000-line program and it doesn't do what you're supposed to do. You don't just delete it and start over. You start probing it. You start looking at what's happening at different points in the program and trying to narrow down exactly where the problem is. That's what we can do with this. So this is going to be really important. All right, the last piece of your schematic is the project ID block. And I would put something like, sample circuit engineering 250, and I would put down the date, which is 22 March 2024, and I would put down my name. And then, in the workplace or something, once you have this design, somebody would look at it and they would approve it, and they would say, yes, this is a good design, and then there'd be another line, maybe multiple lines for approval, and somebody would write their signature there. And now if you finish your whole design process and you've got your final product and it's not working, and it comes back down to where, you know, there's a problem with this, they can say, well, who approved this design, right? And they'll call, you know, the engineer and the approver in and figure out what went wrong and try to improve the process. All right, so there's a schematic diagram, and you'll get a lot of practice making these diagrams in the practice problems and also in the labs in this course. All right, so next class we're going to talk about the complement of sum of products, which is called product of sums, and we'll start talking about how to simplify expressions so that instead of having something with, you know, 5 product terms all ORed together, maybe we can compact this into something simpler, which will end up leading to a circuit with fewer components. Fewer components, less costs, less chance of failure, smaller size, and so on and so forth. All right, so we'll get into that next class. Thanks.